And in 2016, world's data centers, that is, this contain massive monoliths of servers and switches, they consume almost 40% more electricity than the entire United Kingdom. And now you have a continuous demand for increase of bandwidth or bit rate. So what is that? You need high definition television. So in that case, if you want to transmit or use or process high definition television signals, then the conventional copper cables will become ineffective. So this gentleman, Dave Miller in Stanford, he worked on that, and he proposed that, well, he said that even at the gate level, the main driver of energy dissipation is the capacitance of the wires being charged and discharged. And at the data center level, the largest server farms may consume an entire power plant's worth of electricity. So the efficiency of server-to-server interconnects poses the boom in silicon photonics, that is the photonic interconnect based on silicon platform. So here is a comparison between electronics versus photonics. You can see this red and green naturally indicates advantages and disadvantages as usual. For electronics, a speed limit is a limitation, but for photonics, high speed is the characteristic. For electronics, you need metallic layers and these insulators in between, as I have already shown you. But light beams can cross without interference. That is the advantage. In electronics, too much power dissipation. In optics or photonics, less power dissipation. However, these are the advantages. For electronics, size is too low, less than 10 nanometer, as I have already pointed out. But for photonics, there is a fundamental limit of physics, diffraction limit. Size is too high, and the size is wavelength divided by refractive index of the material. So is larger than 200 nanometer. Compare this 10 nanometer at 200 nanometer. So photonic devices or photonic integrated circuits, so to say, will have a larger footprint. And for electronics, there's a possibility of monolithic integration on silicon that is well established. But for photonics, there are difficulties. You have to take recourse to heterogeneous integration on different platforms. The reason is silicon is poor emitter. You cannot achieve LEDs or lasers by using indirect bandgap silicon. There is no electro-optic effect, and that is used in modulation. And modulation bandwidth is enormously low and cannot, for bandgap, the silicon-based devices cannot be used for 1550 or 1300 nanometer for the standard optical fiber communication. So here this slide indicates how we are moving from copper interconnect to optical interconnect. In copper interconnect, there is chip to chip. And then in the optical domain, now you have rack to rack or board to board. Then within a metro and long haul network, instead of using HDMI cables, you can use optical connection links and so on and so forth. So, but the distance covered is quite limited. So let me give you an idea of silicon and group 4 photonics with its advantages. This is the left-hand side is already shown. And within a computer, between cards, you can use optical interconnects to save energy and to make speedier. Then you can use fiber to the home, that is optical communication by using fiber to the home. And then you can replace copper interconnects in VLSI. This is already illustrated. You can use this. And many industries are interested: Intel, IBM, HP, Kotura, Sun, IMEC, non-profit organization, ST Microelectronics, Alcatel, Thales, Nippon, Hitachi, and there are new companies which has been bought by different companies like Cisco or Google or many other things. And there are different government funded projects to develop silicon photonics. And these are some examples. And this European Union, UK. Then there is a European project Platon. It contains surface plus one plus silicon photonics. I will come to that. Yeah, there is a inter country collaboration boom between Germany and Italy. And I mentioned that IEEE Photonics Society holds annually Group 4 Photonics Conference for over 10 to 15 years, and it has been renamed as a Silicon Photonics, this conference. This year it will be Silicon Photonics. But there are developments, but there is still many things to go that I'll tell presently. And then, I discuss what is happening nowadays. So, is the artist's view of silicon photonics, and it integrates silicon photonics integration on same platform. Well, I forgot to mention that, well, how this silicon photonics or optical interconnects work, I'll discuss, I'll explain in the next few slides. But I forgot to mention that even if you have electronic integrated circuits, that is DSP and all that, which is needed for processing, ultimate processing this into electronic domain, and then you have to process this by using usual a silicon integrated circuit. So you have to make a combination. So these are some examples, that is silicon, photonic, and electronic chip is one example. Is and is used in backplane and display interconnects, as I have already mentioned. It can be used in medical lasers. It can be used for chemical analysis, and naturally is chip-to-chip interconnect, as mentioned, connection between one chip to another chip, and already it will be used in data center between servers, which consume a large amount of energy and power, and to reduce that energy consumption, you use optical interconnect. So how is that optical interconnect work? Basically, it's the same. I know all of you are familiar with optical fiber communication. So this is the basic, and this is illustrated. The basic principle is illustrated. Simple communication. You know, in communication, what you need a transmitter, and then you have a receiver, and you interconnect this transmitter and receiver by a medium. For free space communication, you use antenna here, and you use antenna in the receiving side. But in case of optical communication, this transmitter and receiver are connected by a medium, which by this time, you all know that is optical fiber. Or maybe it may be free space communication, but forget about that. Optical fiber. Optical fiber is nothing but a waveguide. It's a cylindrical waveguide. But in silicon photonics, it's the same waveguides are used, but these are planar waveguides. Well, you know, enormous improvement in the optical fiber communication. That is, you use this fiber optic communication links to receive and to transmit our voice and our text, then video and picture. And I want to make telephonic conversation with my friends from Calcutta, Kolkata to London, New York, and everywhere. And we increase the capacity, transmission capacity of this optical fiber, single optical fiber by using a technique which is known as wavelength division multiplexing system. Frequency division multiplexing system is taught in communication, basic communication. For optical communication system, this is the same thing. It's named differently. It's called wavelength division multiplexing system. This is an example. Here you have your computer, and then you send your data, that is your email or voice, text or video by some means to the local optical center, and your data, like say 10,000 or 20,000 or 1 billion subscribers, modulate one laser, and maybe one laser is modulated by combining all these signals at a speed of 40 gigabit per second. Well, that is the standard technique. Now you employ a number of such lasers, right? So lambda 1, lambda 2, lambda n, each modulated by 40 gigabit per second. And if you use 100 such lasers, then you can transmit data at the rate of 4 terabit per second. Terabit is 10 to the 12 bits per second. So what do? You combine all these modulated signal by a multiplexer, and then you transmit this through a section of the fiber. It gets attenuated. You use a amplifier, which is called fiber amplifier. You use another section of fiber link. Then it comes to the receiving side, maybe your friend in New York. So you have to demultiplex this by the local station, and by demultiplexing, it is sent to different detectors, 100 such detectors, and your friend's network is connected to one such detector, and he receives that signal which you have transmitted from your end to your friend at New York. He gets your email, he gets your picture, or he just makes some conference, video conference with you. So that's the technique, and this technique, that is wavelength division multiplexing, and this basic optical fiber communication, replacing the optical fibers by say waveguides is used. You just scale down. Is say 5,000 or 6,000 kilometer, or maybe more than that. But in your case, when you talk about silicon photonics, or when you talk about photonics interconnect, this is scaled down to say a few millimeters or few centimeters at most. But the same technique. Okay. Now, how this integrated circuits or photonic integrated circuits? There are two competing materials, and usually in optical fiber communication link, you have to use indium phosphide as the substrate, and you have to have, you can grow everything because indium phosphide is a direct bandgap material. You can have laser, you can have modulator, and you can go everything. You can have waveguides, you can grow everything. You can grow it monolithically, but the price you have to bear is this is an expensive material, and is a small wafer, 75 millimeter typically. But if you compare this to silicon, silicon is comparatively cheap, high yield. The processing technology, as I have mentioned, is quite mature for 60 years or so. And a large wafer is 300 nanometer or 450 nanometer, as I have already mentioned. But the difficulty, as I have said, that with silicon, you cannot grow any laser. Modulator is not very good. Is not very effective. So in spite of that, I shall not discuss the basic principles. In spite of that, there are remarkable progresses. And in this case, in this slide, I will show you some examples. Is the left hand side is a modulator. That is, what you do in modulator, what do? You just change a part of the active device, the refractive index of the active device, and you compare this with the unmodulated part. So the phase change makes some change in the output, and this phase change modulates, that is this impress signal at the input end, and so is maybe amplitude modulation, or it can be used as a switch. You can either make this signal on and off according to the digital signal impressed at the left end, that is the input end. Remember that digital signal, these digital signals I am mentioning, is in the optical domain. That is, you use electronic digital signals, you convert this to the corresponding replica of optical signals, and then you transmit this by different photonic devices, and you get this digital signals at the other end. So that's the function of the modulator. And when you receive that digital signal at the opposite end, what is needed? You get this in optical domain. There may be some amplification. Forget about that. This optical signal must be converted into corresponding electronic signal, and so that function is performed by a photodetector. What is the function of the photodetector? It converts optical signal into corresponding electrical signal. Naturally, you know this figure of minutes. I am not going into these details. And in that process, well, these signals might be weakened, might be distorted. So you need an amplifier, or you need a laser to produce these digital optical signals. And I shall not mention there.
2 dB per centimeter is optimizing which law?
Sorry? Sorry? Hello? Hello?
Which sort?
Yeah, any question?
Yeah, sir. Answer like
Question?
2 dB per centimeter is which sort of laws here?
Sorry? Can you ask this question at the end of this talk? But I am unable to follow. There is some network problem.
Please ask the question at the end of the talk.
Okay.
Do you hear me?
And put the question in the chat box also.
Yeah. Can you hear
Please
me?
put the question in the chat box.
Can you hear me perfectly?
Sir, please continue.
Yeah, yes, sir. Continue.
Yeah.
Okay, so should I continue? Yeah. Okay, so these are some examples of the active and passive devices which are used in making this photonic integrated circuits. These are different. The lower part, that is bottom part, indicates the waveguides. Well, it may be is used silicon and silicon dioxide. Silicon dioxide is the insulator. Silicon nitride is the insulator. Silicon oxynitride. Even you have a silicon rib. You have a buried channel as shown in this figure, and you can grow this on glass. What is the principle of waveguiding? You know from optical fiber that you have two different layers. One is this is a core whose refractive index is larger, and it's covered by cladding whose refractive index is lower. So if you apply the principle of ray optics, that is total internal reflection, if you launch some light at the input end, it gets reflected by total internal reflection, and it's transmitted from one end to other end. So that's the technique. So you need two different layers, having core as with higher refractive index, and cladding as a lower refractive index, right? So that is cylindrical. Optical fiber is a cylindrical waveguide, as I mentioned. And here in this planar waveguide, you have the core layer with higher refractive index surrounded somehow by a layer of lower refractive index. That's the basic principle. So it can be grown in different ways, and here are different geometries by which you can realize the optical waveguides. And now I come illustrate a very different is a complicated thing. Maybe if you ask me questions at the end, then I will give this answer. I am not going into the physics because it will involve a lot of physics, and my time is almost when I have covered most part of my talk. So here you have different
এটা যে
types of
স্কিল
modulators.
ডেভেলপমেন্টের আগে একটা
In the
এন্ড
B, yeah, sorry, in upper part we have different configurations of modulators based on different principles. One is injection of carriers, which changes the refractive index. Carrier deflation again changes the refractive indices. There is metal oxide semiconductor, changes the refractive index. Then well, you have to apply this signal, digital signal, as shown in this figure. You can use another physical principle by using a quantum well structure, silicon and silicon germanium quantum well, that is called quantum confined Stark effect. Is too much physics. If you are interested, I'll try to answer that. So these are different configurations of modulator. And the lower part, that is B, you have different parts of photodetectors. And photodetectors you are familiar, and you teach your students by using different configuration. Here is PIN. You have MSM, that is photoconductor type of photodetector, and you have avalanche photodetector. So these are different geometries. These are used by different people and by different vendors. Okay, so I cover waveguides, modulators, and detectors. Similarly, you can have Y junction, you can have P junction, you can have different kinds of gratings by using these waveguides. Now, the best, this is difficult part is light sources. Well, I told you already that silicon is an indirect bandgap material, silicon, germanium, and group 4. These are indirect bandgap materials, and they are poor light emitters. So that's the problem. You cannot realize efficient light emitting diodes or efficient lasers for your purpose, for your communication. And as I have already mentioned, in present day optical fiber communication systems, light sources are grown on indium phosphide. Indium phosphide is a direct bandgap material. Here you face difficulties. You have monolithic integration. It's called germanium laser, but that is still under development. Room temperature continuous wave operation is yet to be achieved. And what do? You grow everything on silicon platform, that is modulator, detector, waveguides, interconnects, everything. At the same time, you grow your digital signal processor by using silicon. In your silicon ICs, you use the same processing technology. That is the advantage. But you have to make a sacrifice. You have to use the lasers which is grown on 3,5 compounds, and somehow you have to couple these lasers with the rest of the integrated circuits. Okay, so that's the problem. So that is called the hybrid integrated circuits, electronic photonic integration, hybrid electronic photonic integration, that is being used till today. But the laser action in group 4 material, for example, germanium silicon alloy on silicon platform which can be grown, it shows a direct bandgap nature for alloy composition by applying strain, but it's still a long way to go. So here is an example of a transceiver, and this is grown on the same chip, silicon photonic integrated circuits. This is the transmitter side, and this is the light input side. This is the receiving input side, and you can see that 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 1 into 8 multiplexing, right? Wavelength division multiplexing is done 8 times, so you can increase the speed of operation. And similarly, in the receiver side, you have this 8 into 1 demultiplexer. This is a picture of this silicon photonic integrated circuits compared with a coin in US dollar. So it's almost comparable, and you can gain in size. So that's the story. This is another transmitter chip developed by Intel. So as I mentioned, 1, 2, 3, 4, 4 different lasers working at different wavelengths or different colors, and each modulated by 12.5 gigabit per second data. So these are well modulated. These data are fed to the individual modulator. So each laser signal, laser wavelength is modulated 12.5 gigabit per second, and these 4 modulated signals are wavelength division multiplexed by multiplexer. The combined output is fed to a section of optical fiber, small optical fiber. So combined bandwidth is 50 gigabit per second, and the other side contains a receiver. So that is by Intel. I just show you the examples of different configurations used by different photonic integrated circuits, and this is the figure 2.10, that is this one which I am showing, is a kind of modulator which is called Mach-Zehnder interferometer modulator. This is unchanged, but the other end, this is the other arm, is some kind of refractive index change is introduced by applying electric field on that. So that produces a phase change between this arm and this arm. So in the output, you get some kind of intensity modulation, or you can have even on-off modulation. This is electric indicated in this signal. So optical input, you have 2 arms of a Mach-Zehnder interferometer. In one arm, you produce electrical digital electrical input that changes the refractive index of this material, converts the properties of this arm, and when combined in the output side, they produce this on-off keying, which is the exact replica of the electrical input. That is one example of how this modulation is done. There are ring resonators and all that. I don't want to enter into these details. But I come to the last phase. There are some limitations of photonics. Well, what are the limitations? First thing, heterogeneous integration, emitter 3-5 semiconductors, and processing electronics on silicon. Well, these are combined by a technique known as flip chip bonding. It degrades performance. Germanium tin laser is still a long way to achieve. Then there is the fundamental limit of size limit, that is fundamental law of diffraction. Size cannot be less than the wavelength by refractive index. I mentioned that, and that is the fundamental limitation. So photonic devices at best 200 nanometer, and you cannot go beyond that. But the electronic devices, you can already achieve 3 nanometer. So forget about 3 nanometer. Go to say 10 nanometer is 1 order of magnitude still lower. So enormous size mismatch between difficulty in achieving electronics photonics integration. So you can see you have to be satisfied with a large size mismatch between your electronic signal processors and photonic integrated circuits. But the size of the total integrated circuits will be quite large, as when this is contrary to what you find in your computers, in your laptops, and in your mobile. And speed limit due to inherent low modulation bandwidth of lasers, that is 60 gigabit per second. It can be increased at the cost of wavelength division multiplexing. But the current and future demand for bandwidth, I mentioned that not only in data centers and high performance computers, but also in networking, that is 5G and 6G mobile. There will be more, it's anticipated that there will be more demand with spread of artificial intelligence. And so there is a need for faster and greener. Greener means less power consumption, less energy dissipation. Requirement set is 10 picojoule per bit at peta, that is 10 to the power 15, or exa, that is 10 to the power 18 flop rates. So that is a very stringent requirement. So what is the whiteout? That has been set forth. You see that this is the remedy comes in terms of plasmonics. So here is a comparative figure, is a dimension and the operating speed. Electronics is dimension is very low, as I have mentioned, but the operating speed is not large, is limited by that. Forget about the past. You come to photonics. In photonics, you can increase enormously the operating speed. In fact, you by using wavelength division multiplexing, you can increase this data transfer at terabit per second, or even larger than that. But the limitation is that size is enormously large due to fundamental physical law, that is diffraction limit. And the best combination will be in plasmonics, that is by replacing electronics and photonics by plasma waves, plasmonics. It shows promise for high speed. At the same time, you can reduce the size of your device beyond your diffraction limit, that is sub-diffraction limit. So what is plasmonics? Forget about that. This is a projection of the speed. What is plasmonics? Plasmonics is quite well known. Is in Lycurgus gap, which is kept in British Museum. 4th century AD is King Lycurgus. He is seen being dragged into underworld by the Greek nymph Ambrosia, who is disguised as a vine. So you can see this is a cup kept in British Museum. It's a glass cup which contains particles of gold nanoparticles, So if you view this in reflected light, that is daylight, you can see the color is green, but if you shine light into the cup, you see there is a change in color. So that's well, people didn't know that, and they use this in medieval churches using different particles of silver, gold, and copper, and they could create the pictures of Mother Mary or Jesus Christ or different stories of Bible by using the different metallic nanoparticles. So plasma waves, in plasma physics, waves in plasma are an interconnected set of particles and fields which propagate in a periodically repeating fashion. A plasma is a quasi-neutral electrically conducting fluid. In the simplest case, is composed of electrons and a single space of positive ions, but may also contain multiple ion spins. Forget about that. A plasma is created by electrons and positive ions. So just take this classical picture. So what here? You have a metal and you have a dielectric material, say maybe air, maybe some insulator or whatever be it, and you shine light. So this light will create will create some disturbances in the material, and it will attract electrons, and by the same process it will make diffusion, and so it will create alternate regions of positively, that is the positive ions of metals, and the negative ions, negatively charged particles, that is electron. So you can see that this is the variation of electric field between this dipole, that is positive charge, and negative charge, and so you can see this, and so you can create a plasma wave by shining light on this metal dielectric combination, and these plasma waves they are time varying, and at the same time it propagates. So this is illustrated by this. Is again illustrated by this figure. So is plasma waves propagates along this direction as the direction of propagation. Now, why do we call this plasmon? Because it's a plasma wave in the classical sense, but in classical sense, wave can be converted into quantum mechanical sense into particle. There are many different examples. For example, electromagnetic wave in classical physics is called bunch of photons in quantum physics. Lattice vibration waves is in classical mechanical waves. In quantum mechanical language, it's called bunch of phonons. And so if you have surface plasma waves, this propagates along the interface between metal and insulator, surface plasma waves, so you get surface plasmons. And there are many complications, forget about that. So it's illustrated in this. Well, time is limited, so I won't go into this exercise anymore. You have to you have to do this, create or excite these plasmon waves in a metal insulator interface by using two different techniques. One is prism, and another is grating. So this is a variation of the intensity electric field within the insulator and within the metal. And in metal, this variation is known as the variation depth or penetration depth. Is called the skin depth. And insulator is also it decays exponentially. And at the metal insulator interface, the electric field is maximum, and it propagates along the propagation directions. But unfortunately, this propagation direction is quite low, maybe a few nanometer. But if you want to have this, and what is the beauty? Well, I forgot to mention that this calculation shows that if you shine light, say blue light, and you can create surface plasmon waves whose wavelength is less than the wavelength of blue light. That is, if you shine with 400 nanometer, the plasma waves will have a wavelength less than 400 nanometer, and so that is called the sub-wavelength operation, and that solves your problem. If you design your structure and if you design your systems in such a manner that by using photonics, by using photons, you can create a wave which is surface plasmon waves, whose propagation length is quite low, sub-wavelength, and you can make devices, or you can have amplifier working at this sub-wavelength regime. But its bandwidth is enormously large, and at the same time, its size is limited. So that's what people are trying to find out. That's what people are trying to find out. So this is an example. I shall not describe this propagation length in this example. Numerical example shows 10.1 nanometer only, but ultimately you have to have a waveguide which will connect between one device to another device or one system to another system by using a plasmonic waveguides. But if you have only 10.1 nanometer, but your server to server distance is say a few meters, then how it can work? So you need some kind of amplifier. So this is an example of plasmonic waveguides. It's just like dielectric waveguides, which photonic waveguides I have shown. Instead of two dielectric materials, you have plasma and an insulator. There are different configurations. Many of you are familiar with that. You can use this. You can have these different gates. And then the question of amplification. So I just told you that from one server to another server, the distance may be a few meters, but these plasma waves can propagate all, say a few hundred nanometers. So the whole purpose is lost. So somehow you have to amplify your surface plasmonic waves, and there is a concerted effort to have a new kind of laser, plasmonic nanolaser or spacer. What is spacer? Surface plasmon amplification by stimulated emission of radiation. Unfortunately, I don't have time to discuss. It's too complicated. Here are some examples which establish that spacers can be achieved. Is 2009, and already much progress has been made. There are some examples of this electronic, plasmonics, and photonics integration. Platon is a European project between Germany and Italy, There are some examples. Time is limited and the speed is calculated or projected. Here are some examples, but it's still a long way to go. So I come to the end. Requirements for greener or faster network on chip. I have already mentioned that demand for bandwidth is increasing because of 5G, 6 networks and artificial intelligence. At the same time, you have to reduce the energy consumption, energy efficiency. You have to increase the data rate enormously. So that's the story. And at present, well, this is hybrid electronic photonic integration, in some cases plasmonics, but plasmonics is not progressing well. It will take a few more decades to be mature, but that's a research area, current research area. So I can summarize. Initial work on miniaturization of IC is presented. Current problems of energy dissipation and interconnect bottleneck has been discussed. Role of photonics, in particular silicon photonics, in solving the problem has been discussed. Large footprint of photonic devices due to fundamental diffraction limited point out. The problem of electronic photonic integration discussed. Surface plasmonics seems to be a better solution, and there are amplification spacers is still immature. And finally, the aim is to integrate everything. We have electronic, photonic, and plasmonic systems, hybrid systems maybe. So, with conclusion, amplification of plasma still at infancy. Integration of electronics, photonics, and plasmonic systems has started. Hybrid systems will be in use for some more time, and let's wait for the green revolution caused by plasmonics. Some references are given. So thank you, and take care and stay safe. So with that, I once again thank you for your patient hearing, and questions, please.
Thank you, sir. Thank you very much for this wonderful, informative lecture. Now the participants, sir is here. If you have any queries, please feel free to ask.
Somebody asked one question. Unfortunately, I asked him, requested him to put that at the end of this talk. Can you repeat?
Sridipal sir, you are not audible.
Hello, can you hear me? No, I'm not asking anything.
Yes.
Mr.
Please.
Mr. Pankaj was asking some question, I think.
Yeah, what is that?
Yes.
This is Chawla.
Pankaj Chawla. I think you were asking question.
Can you
Sir, so I'm asking like what sort of softwares I can deploy for the photonic construction and sort of stuff, the interconnects and the chips and sort of stuff. So
Well, where we can apply? Well, it's already in use. I told you that Cisco, Google, Facebook, and all other data centers which handle a large amount of data. And these are, well, the everybody's and everyday's experience. They use high performance computers and they have their huge data centers. They are already using that. This electronic photonics, that is silicon photonics, they are already using that. So I thought that I should include the list of vendors or list of the companies which are involved in this game. And of course, as I mentioned, the plasmonics, it has come out, but this is still at the research stage. And these companies are also trying, and that they are trying to meet the requirement. That is the exaflop the rate of high performance computers, and also the lower power consumption, that is 15 picojoule or something like that per bit. So that they are trying to reach that. So this is already in use. All the large companies. I repeat once again, Google, Facebook, Cisco, and what else? These companies those companies who are all Instagram, etc., etc. They are using. They are high performance computers. So there's large servers, and in order to reduce power consumption, all that, they are already using this kind of things. Okay, so just to make things clear, recently you have seen that there is chip shortage. You read, every day you read in newspapers that there is an acute chip shortage, and to mention that these chips are mostly produced by Taiwan Semiconductor Manufacturing Company. That is the first top, and second one is Samsung, and in some part it's not IBM and Intel. They produce their own chips for their own purpose. Okay, Intel is entering into mobile business, but all those chips, everything which is used in computers and in mobile sets, these are supplied mostly by Taiwan Semiconductor Manufacturing Company and Samsung. And what you do, many universities and many educational institutions, they have their VRSI design programs, is software oriented. So they make those design. Then they ask these manufacturers to produce their integrated circuits. They produce and supply the back, and they make the different integrated circuits, and somehow it's going on. And now we have heard that India is this Foxconn is Taiwan Semiconductor Manufacturing Company, and Vedanto is not Vedanto, a wing of Vedanto. They are entering into a project, and that will be that project will come into shape in Gujarat. So you have read in newspapers that there is some kind of fight between Maharashtra and Gujarat. Ultimately, it is decided that this project will start in Gujarat. So that is the Indian thing. And perhaps you know that the government of India, DIT, that is Ministry of Information and Information Technology, they have launched a program which is known as the Special Manpower Development Project. They have awarded project to different IITs, NITs, and universities. Our university is included, Calcutta University is included. That is, you have to develop analog integrated circuits. You have to make your design, supply this semiconductor complex Chandigarh, and they make these devices, and you can use this. Many Indian universities or IITs, they are producing this integrated circuits, and they are using this for their own purpose, or they are supplying to different mostly analog, but it's not that in 3 nanometer, maybe 180 nanometer, or maybe less than that. So that's the state of the art in Indian scenario. Any more question? Yeah. Any further question?
Dikta, continue.
Sorry?
Hello, Dipta.
Dikta,
Dipta?
please unmute yours.
Dipta, please take the mic.
Dikta, please unmute yourself.
Dipta, please take the mic.
Dipta, please unmute.
Okay, sir. I think there is no more questions. Thank you, sir. Thank you very much for this wonderful session.
Ma'am, I have a question.
Yeah.
For the photonics, what would be the RC delay value? What would be the thumb of rule?
Sorry.
Sir, there is
Please
a
repeat
question from
For the photonics, what would be
Chawla,
the
sir.
RC delay rule? What would be the thumb of rule of its specific value?
Well, I mentioned that, it's depends on time delay, and that is velocity of light divided by diffractive index. So just calculate. Certain, yeah. So if your light is say, it's usually 1550 nanometer. So convert this to frequency and take 100%, say 10% bandwidth, and that will give you an idea of the better. It is say maybe 10 to the 15 beats per second. Maybe 10 to the 15 beats per second. 10 to the 15 beats per second. Theoretical limit that has been achieved is maybe 35 or 50 terabit per second. But by using optical fiber. The optical fiber has bandwidth that large, 50 terabit per second or something like that. Is your question answered?
Professor Basu,
Yeah.
Yes, sir. Yes, sir.
I
yes.
just wanted to,
Yeah.
hello.
Yes, please.
I just wanted to say that there is one very important aspect that probably you have overlooked because of the shortage of time. But I just wanted you to the difference in latency when the bit stream is in bit parallel compared to byte parallel.
Yeah.
When you go from electronics to photonics to plasmonics, there's a very huge problem in that particular area.
Yeah,
Can you
that's
throw a
true.
bit light on that?
That's true. That's true. I agree. Yes. Thank you. Thank you for pointing out this. Thank you. I agree.
No, sir. Welcome.
Yes,
Welcome, sir.
I just wanted to cover a wide area just to introduce what's happening to the young mind.
I congratulate you for the enormous amount of range you have covered. Phenomenal. Phenomenal.
Thank you very much.
Thank you so much.
Thank you, sir. Thank you, Professor Kak, and thank you, Professor Dr. Prashanta Kumar Basu, sir. Professor Basu, your screen is shared till now.
Sorry? I don't follow. What? Is it okay?
No, sir, there is a stop sharing option.
Oh, I see.
Below
Stop
here,
sharing.
stop presenting. Yes, sir.
Okay. Thank you. Thank you. Bye.
Okay.
Thank you very much.
Thank you, sir.
Thank you, sir.
Oh, thank you.
I'm sorry that I'll be late in joining the next session. I have some other things to do. Okay. So long. See you again. Badrinath, see you again.
Oh, okay. See you. Thank you very much. Thank you.
Should we go for the next session, sir?
Yes.
Yeah, I think you should go for.
Sir, our next session is, will be taken by Professor Dr. Subroto Kaur. Sir, are you here?
Yes,
Professor
I am.
Dr. Subroto Kaur?
Yes, I am.
there.
Okay. Okay, sir. Welcome, sir. Professor Dr. Subroto Kaur graduated with honors in electrical and electronics engineering from the Birla Institute of Technology and Science, Pilani, in 1987. He holds a doctoral degree in electrical communication engineering from the Indian Institute of Science, Bangalore, in 1991. In 1994, he joined Indian Institute of Technology, Delhi, where he is presently a professor at the Department of Electrical Engineering. He holds the Ram and Sita Sabnani Chair Professorship at IIT Delhi, and his research areas are in optical communication, switching access technologies, telecom protocols, embedded systems, and high-speed networks. Professor Kaur will give his lecture today on some applications of sensor networks. Welcome, sir.
Thank you so much. And good morning to all of you. I
Good morning,
am
sir.
sharing a window. I think I'm sharing a window. Let me see whether I'm okay. Do I have presenter rights? Because I'm unable to share my screen.
You can share.
Sir, you can present the slides.
You can present that.
Are you able to see any screen of mine?
No, sir. Till now we cannot see anything.
No, sir, it is not
It
visible
is-
now.
It is saying your browser can't share your screen. So that's an issue. So exit full screen.
So you go in a different browser.
Okay, all right. So I'm just logging out from here.
Yeah.
Okay, I'm sharing my screen again. And are you able to see my screen?
Yes, sir.
Good. All right, so I don't know whether I should go into the slide mode. Are you still able to see my screen?
Yes, sir.
Are you able to see two things on my screen or one thing on my screen? Two things.
Two things,
Both
sir.
the thing is here. Both the thing.
So you're seeing the wrong screen.
The two things we can see. Yes, sir.
All right, that's the. This is. I think that would show you the right screen. Are you seeing the one screen?
Yes, sir. Yes, sir. Yes. Only one screen.
Yes, sir.
I wanted to say thank God, but it's actually thank Bill Gates and Sundar Pichai. Okay, can the rest of us mute ourselves? If
Tapu
I think
sir,
we
please
have
unmute
one
yourself.
people who are unmuted. Okay, okay. I think they have muted themselves. So my talk is on smart sensors, right? And a part of what I'm going to say is that sensors can come into most physical aspects of our lives. And we already have sensors which in our lives anyway. For instance, when we toast a piece of bread, there is a sensor which senses how long you have been toasting it and then pops up your toast. There is a sensor which says, do you want it toasted very much or very little or not at all, right? There is a sensor which is in your microwave which says you have been heating this thing for 30 seconds, 45 seconds. So all of those are sensors. They are not smart sensors. Right? For instance, your microwave's 30-second sensor is set by you, right? So whether you have 2 kilos of food in your microwave or 1 gram of food in your microwave doesn't know about it, right? It should, but it doesn't. Right? So that's what I mean by the word smart sensor. Right? A sensor which actually has some idea about what it is sensing and how to change itself accordingly. Right? I tried to make my slides as simple as possible, right, without losing the essential aspects of what I'm going to talk about. Right? So, what do we sense? We sense our world. Essentially, we sense our world, right? When you are sensing your bread, piece of bread which you are toasting, if you are sensing that, it is your world. It is your kitchen world. Right? If you are sensing the temperature of the air outside your window, maybe because you want to know the weather outside your window, that is also your world, right? The question is, when you sense the temperature of the air outside your bedroom window, can you change that temperature? No, you cannot change that temperature. You can merely read that temperature, right? So there is nothing you can control about that temperature. For instance, you cannot turn an AC on and cool Kolkata down or Durgapur down by 2 degrees centigrade. But very often we want to do that. We want to react to what we sense. So if the room is at 29 degrees centigrade, we wish to run the air conditioner for an extra 20 minutes so that it comes down to 24 degrees centigrade. So that is controlling the temperature. So we wish to control or actuate the space we live in. Right? So when we control, that's an output. So we not only want to take an input from the world, I'm saying a input from the world, but it is many inputs from the world. I could sense so many things from the world: humidity, temperature, pressure, stock markets, number of COVID cases. I could sense a lot of things from this world, but there are only a few things I can control, right? So we wish to control and sense the spaces we live in. I have summarized it in this slide, and I'm sure that it's a very simple slide, but look at just focus on the right hand top corner of this slide. So I'm sure you have read this as a prayer somewhere. All things bright and beautiful, all creatures great and small, all things wise and wonderful. Okay, the Lord God made them all is controversial. For a scientist, it's controversial to say whether, well, if God exists, then he made them all, right? He or she made them all, right? But that last line is controversial. So we can say that, okay, anything in the top 3 lines, all things bright and beautiful, right? Things, passive things, right? We can measure. all creatures, great and small. They also can be measured, monitored, controlled, right? So I'll just talk about that. And all things wise and wonderful, that also we can sense and control, right? And you can see that, okay, let me take this out a little bit. Lord God made them all, but we added sensors to this whole set of things, right? So let's look at all creatures, great and small. That happens to be the leftmost window out here, right? What do you sense out of these creatures, right? I have sort of sorted them, right, in the order in which they roam this world. For instance, fishes, right? Fishes like dolphins, sharks, etc., are deep sea fishes. Then there are fishes which we catch. So there's a fishing hook here, and fishes we catch, right? And there are fishes which eat other fishes. Right? So this is almost the water level of this planet, right? And just above the water level of this planet, you have turtles, you have tortoises, you have olive ridleys, you have animals like tigers, zebras, beavers, elephants, vultures, bats, koala bears. Right? Now, what do you sense about a fish, let's say? Right? So this is a very funny slide to put in a faculty development program, but what do you sense about fish? Well, the thing is, what is there to sense about fish? What do we want to do with fish? Number one, we want to catch more fish. Right? So if you look at this fishing hook out here, we wish to catch more fish. So if you want to catch more fish, what do you do? How do you go out and catch more fish? Well, number one is you can depend on rumor. One fisherman comes and tells another fisherman, I think there are going to be more fishes if you go in the southwest direction today. So you just believe that person and sail in the southwest direction, believing that you will get more fish. But what if you don't get more fish? Well, then you come back and you keep listening for more rumors, right? No, so your sensing of this world is through rumors. But you can't fish with rumors. I mean, you're going to be out of your business. I mean, you're going to make a loss very soon, right? So what would you like to do? So what does India do? Do Indian fishermen sit on the coast smoking a bidi and asking other fishermen, where do I go? Do I go north or south or east or west? No, they don't. So ISRO actually sends up satellites which have cameras mounted on them, which have different penetration depths when they look at the oceans of India, right? So they look at the coasts of India, they look at the blue waters of India, they look at the littoral oceans of India. And those satellites, because they work at different spectral bands, they can have a penetration depth which allows them to say, oh, here there is a school of fish, right? A group of fish, which is about 1 mile wide and 6 miles long. So if you go in this direction, and this is the advice they give to all Indian fishermen, that if you go in this direction, you are going to catch a lot of fish. Now, this sort of an advisory, who is the censor here? The satellites, CMOS, deep infrared, near infrared, long infrared cameras made by Indians, for Indian fishermen, right, is the censor. So ISRO sends up these cameras into their satellites so that they can watch the oceans in the morning, 2 hours later, 2 hours later after that, and advise fishermen in which direction they should go. And that maximizes the fish catch. Now, don't you think that the actuation is go in that direction because there are fish? So that's a sensing system, right? Just look at this Matsya Nyaya, what we call in Hindu philosophy, Matsya Nyaya, a small fish being eaten by a bigger fish, right? Now, suppose this is the fish, which is a dangerous fish, right? You would like to look that if there is a beach, right? Let's say Digha beach, and there are a lot of people shouting, jumping, playing, having a picnic, generally having a ball, and somebody sees 5 sharks. Don't you think the people on the beach need to be warned that the sharks are very close, maybe half a mile away, and you need to get out of the water fast? Right? So don't you think that's a sensing system? Whether you stand on a platform and look at the sea and watch for sharks, or you spot the sharks through a GPS collar mounted on each shark, or you watch for sharks from a satellite, whichever way you sense the shark, don't you think the actuation is asking the people through some mechanism, maybe shouting through a loudspeaker, that get out of the water is the control? So that's a sensor system. So that's a smart sensor system. But suppose you see the shark is there, but the shark is 25 miles into the ocean. You are still seeing the shark, but it is not very advisable to tell people in Digha to get out of the water, because everybody will get out of the water and then nobody will get back into the water. And then the rumor will spread that Digha is full of sharks which eat people. So nobody will come to Digha. So the West Bengal tourism will be out of its business elements, isn't it? So you see that if you do the wrong actuation by looking at the right sensor, you still don't make any sense. So smart sensing was also about sensing the context. We can look at one animal above the water level. Let's say the turtle, right? You know, the turtles come and they lay eggs, and turtles are very endangered animals. So we want them to lay more eggs, right? So they lay millions of eggs, right? Millions of turtles come, maybe about 2 millions, 20 lakhs to 30 lakh turtles come and lay eggs. And this happens over the beaches of India. Now, very often we want to find out, where are these turtles laying eggs? Now, how do you sense where are the turtles laying eggs? So that's a sensor network. Maybe you can take a drone and fly it over the sea and photograph the turtles as they come, and then you can count the eggs. But this is a sensing system which you are looking at. Fine. Suppose you move out of the sea and come to land. This is a tortoise, right? You know the difference between a turtle and a tortoise. A turtle almost lives in the water, and a tortoise occasionally goes into the water, but mostly lives on land, right? So let's say this is a endangered tortoise. Now, how do you know? Suppose you wish to know that in the forests of, let's say, North India, there are 2 male tortoises and let's say 30 female tortoises. Now you can see that you would like to put these two species genders together so that you have a lot of baby tortoises, right? But unless you can motivate the male tortoise and bring him close to the female tortoises, babies are not going to happen, right? So you can have a sensing system which looks at something mounted on the male tortoise, right, to see whether he's coming close to the female tortoises or not, right? So that's a sensing system, right? Now look at this animal, the beaver. You will say that, come on, we are all electronics people. We have been talking about fiber optics, plasmonics, silicon photonics all morning. Why should we talk about beavers, right? Well, beavers are important to be talked about. And remember that I am also an electrical engineer. I'm not a wildlife conservationist talking to you here. Beavers are rather important because they do a lot of things to us, like building dams, which conserve water. So beaver dams, which beavers build, are very important because they put a temporary obstacle to the water, and the water piles up, and a lot of things happen. Trees grow, animals flourish, fishes reproduce because of that damming of the water. Now, you wish to know where is the water damming up, which tree is the beaver cutting and preferring. So beaver monitoring is very important. Right? We are all familiar with this animal, elephants. Right? We know what happens to elephants in Bengal when trains hit them. Right? So suppose you can sense an elephant and then tell the Indian Railways that, okay, there's an elephant, please slow down your train so that you don't hit the elephant and kill it. Right? Or suppose there is a tiger, right? And the tiger has come out of the jungle and is wandering close to the village. If you can sense the tiger, right? And warn the villagers that there is a tiger, don't go out today. Right? I mean, you save some villagers' life. Now, the same thing about bats. Right? Bats have been bad news for the last 2 years, right? Ever since they have been suspected of bringing the coronavirus, right, out of the forest into Wuhan, and from Wuhan to the rest of the planet, bats have been blamed as the zoonotic transmitters of the corona COVID virus. So if you know that there is a population of bats very close to you, you are actually saying what is the risk that this population where they live next to is going to be hit by the coronavirus. So the sensing network here is to see that you avoid this population of bats and interaction with them so that you lessen the spread of a coronavirus. So you can see that it's not just counting bats, not just watching bats, not just putting a sensor on a bat, but looking at interactions between a bat population and a human population so that zoonotic transfers of a disease like corona, for instance, does not happen. And in the top right, top left corner, I have added a very interesting bird, right? Not very interesting to look at, right? But it's called a vulture. Right? You must have seen vultures. I know that in Bengal or in the most parts of India, vultures are very common because people generally dispose of animal carcasses by just throwing them on the side of the road. And these very, very understanding birds come down and they eat the carcass. Right? So that's our disposal mechanism. Right? But something funny happened in India, right, in the last 2-3 decades. The vulture population has almost gone to zero. You see kites, but you don't see vultures. Right? Vultures have declined. Now, why did vultures decline? After all, it's not that animals are not dying in India, they don't have anything to eat. So why did vultures decline? So if you put in a sensing mechanism for what is causing the decline of vultures, you discover something very interesting, a relationship between what is to be sensed and what is happening. What is happening is the vultures are dying. What is to be sensed is, are cows living longer, or are animals living longer? No. So what is causing vultures to die? Well, the reason itself is very, very, very exotic. Apparently, there is a drug called diclofenac. Right? This is the same drug which you have in your Move ointment. Right? When you apply Move ointment to a sore muscle, right? What you have in Move is diclofenac. So diclofenac is administered to cattle. So cows are fed diclofenac because of certain reasons, milk output increases, etc., etc. Now, when these cows die and these birds eat the cows which have been thrown, we don't have any hygienic ways of disposal, so we just throw it and these birds eat it. Diclofenac is not metabolized by the cows, so it goes into these birds and these birds die. So the decline in the population of vultures is because of the increasing use of diclofenac in the animal farming practices. So, then the actuation becomes, how do we ban diclofenac from being available over the counter? So the intervention which this sensor network brings to you is, how do you ban diclofenac? It's not how do you control the death of vultures, it's how do you ban diclofenac, right? So you see that there is a very interesting correlation between what you see, what you sense, and where your control and actuation comes from. Let's move from the water and land animals to the more domesticated animals. For instance, pigs, goats, rams, sheep, cows and bulls, buffaloes, hens, ducks. Now you can see that the way I have drawn this, I have drawn like Noah's Ark. With each animal, except the pig, I couldn't find a male pig and a female pig. With every animal, I've drawn a corresponding male and female gender. Right? That's the orange box which I have drawn around at this point. So you can see the orange box around the bull and the cow. And that's a cow. Now the reason is, why do we farm these animals? It's not that we farm them as pets. Right? We farm them because they give us some economic advantages. For instance, cows give us more cows. Cows have babies. Right? So if you put a male and a female cow together, you get a baby cow, a calf, right? So the more the number of calves, the more the farmer earns, or the richer the farmer. Cows give us milk. Cows give us, well, it's not good form to say cows give us meat, but these animals all give us meat, right? So your kosha mangsho is all from these animals only. So certainly all of you look forward to your kosha mangsho. So maximizing the amount of kosha mangsho, right, the mangsho which goes into the kosha mangsho, is also an important economic activity, and every farmer must therefore try to maximize this, right? So maximizing the number of babies is one thing, but the farmer also wishes to minimize the amount of food you feed to these animals. So what the farmer is trying to do is, what is the least amount of food and medicine and vitamin and proteins and nutrients and living space which I need to give to each of these pairs of animals, so that they give me the most number of babies, the most number of milk, the most amount of meat, the largest size of leather skin, which I can, or largest number of byproducts, right? So this is what the farmer is interested in. This system of animals, right, should reproduce, should not consume too much, should have as many, should be very fecund, very fertile, right? Should have as many babies as possible, right? So that he makes a profit. So profit is the name of the game. Now so where is the sensor network in all this? Well, you wish to know, when is the cow ready to have a baby? So if you can know that, then you can bring the bull close to the cow, right? And then we all know what happens, right? The insemination part which happens, so that the cow then after 6 months or 3 months has a calf. But suppose the cow and the bull don't go on a date, they don't have that calf. And then one has to wait for the cow to again hit a new heat high for the bull to come and visit the cow. The farmer is forever trying to get all his cows pregnant. And this is where a sensor network is very, very useful, because it can sense when a cow is ready to get pregnant. The sooner she gets pregnant, the more profit the farmer gets, because a cow has a limited lifetime, right, in which you can have a limited number of calves, maybe 8 years, maybe 12 years. And in those 12 years, unless you have a calf, the milk output is not maximized. So you have to have a calf at the right time to get the most milk and the most number of calves out of a cow. I know it sounds very callous to say that, right? It doesn't sound very cow friendly, but that's what farming is all about, right? So if you look at these creatures, great and small, in the farm, a farmer can actually install a sensor network to see when this cow should be inseminated, which cow is giving how much milk, right? Which cow is ready to be taken out and made into byproducts. Right? That's a gentlemanly way of saying which cow is no longer giving milk or likely to give babies, and therefore there must be something else on the roadmap of that cow. So all of these things are part of farming, right? Now you may say that, okay, so I have a sensor. What sensor do I put? Well, it depends on what do you want to measure. For instance, suppose you are trying to see whether there is a cow which is giving, which has some infection. Now, if the cow has an infection, it is likely to infect other cows. And if it is infected already, its milk is likely to be infected. And when you mix that milk with the milk of other cows, that entire batch of milk will be infected. And when you package that milk and send it abroad or outside your farm, then it's going to fail tests and the whole milk is going to be discarded. So that's an economic loss. So how do you catch whether a cow is infected? No, that's a sensor. Maybe you can put a plasmonic sensor which changes its output. You remember Professor Basu was talking about plasmonic sensors. So in your milk sensing machine, you can install a plasmonic sensor which detects very small trace amounts of anything. Maybe a contaminant, maybe a bacterial infection, maybe a virus, right? And that plasmonic sensor is going to say this milk is infected. Treat the cow, throw away the milk. Now that's where a sensor comes in, right? Now you can have a variety of sensors. I can think of about 25 sensors which can be installed in an animal farm to sense whether a cow is fertile, reproducing, ready to be inseminated, producing as much milk as she should, growing the right way, eating the least she should be eating, getting the right mix of rations, right? For instance, a pregnant cow needs more of protein. So are we giving her more proteins for the next 3 months, right? A milk cow needs a certain mix of grass and dry fodder. Are we mixing in the right ratio? I mean, all of this can be automated, actuated. And that's the word, controlled, actuated. So if you have cow 1, cow 2, cow 3, cow 4, you don't have to feed the same food to all 4 cows, which is what we do. You know, we have a tub in front of the cow and we mix something and we throw it to all 4 cows. But you know that all the 4 cows have different nutritional dietary requirements. So cow 1 should get more proteins, cow 2 should maybe needs more nutrients, cow 3 is very small, needs more dry food, dry grass, and cow 4 may need more wet grass or more acidic grass. So you can actually customize this very simply using a actuation network. Now, I have drawn a house out here because, you know, these animals which we farm don't live in the open like these wild animals. They live in controlled houses, right? For instance, cows live in barns, sheep live in pens, goats live in yards, pigs also live in pig pens, right? So the house in which they live has a great effect on what these animals produce, milk-wise, baby-wise. So you can install a sensor network in the house in which these animals live so that they are comfortable. Sometimes, you know, you must have seen these movies about cows producing more milk when you play music back to them. And specific musicians, they're very particular about which musician, right? So that's increasing the comfort level of the animal to make it produce more, right? So a stressed animal is not going to produce either good milk or lot of milk or babies at the right time. And this is true for all animals, right? Whether it's a human being or it's a cow, it doesn't matter. If you are stressed, if you are under pressure, you will not perform your best. But if you are comfortable, you will perform your best. So there is a sensor network which you can put into the housing for the animals, right? Which make them more comfortable, and therefore they perform optimally. If you come to all things bright and beautiful, right, you can see that there are plants which can benefit from this treatment too. Right? Plants actually have half of their existence is under the ground from the roots, and half of their existence is above the grounds, right? And human beings are interested in either the part which is below the ground, for instance, potatoes, right? Or what we call colocasia, saru, right? So this is below the ground. And sometimes we are interested in what is above the ground, like tomatoes, like poi, right? Leaves, spinach. Right? This is above the ground. So sometimes our interest is on what is above the ground and on maximizing that, while minimizing what we give to the plant from below the ground. So with the least amount of water, can we produce the biggest, largest amount of fruit, which gives us an economic benefit. So if it was a grape, we would like heavy, plump grapes from which we make a lot of grape juice or a lot of old grape juice, right? Old grape juice is, of course, whiskey, but a lot of grape juice. Right? Or if it was a potato plant, we would like it to consume as little water as possible, right, while producing the heaviest amount of potatoes. And this involves optimizing the amount of water we give it. So we would like the least amount of water. Let's say 10 drops of water per hour. Not flood it. Right? 10 drops of water an hour. Right? Then the least amount of fertilizer. And finally, the most effective way in which we can recycle this plant back into the ground. Right? So this is also very important. For instance, we have a huge problem in winters when the farmers in Punjab start burning their stubble. Right? The entire North India is covered in smoke and smog and fog because of Punjab burning stubble. So a sensor network which can catch, and during the winter months, we get all these photographs in the newspaper about NASA has seen the fires in Punjab happening here and here and here and here. Right? I mean, it's not just NASA, even ISRO sees the same fires, right? But we do sense the fires. And when we sense the fires, we know that it is the farmer who is setting up those fires. Right? So we actually do something about it. We punish the farmer, or we give him something else to do, or we take away his stubble so that he doesn't burn it. Right? So that's the control and actuation which we have to do. We maximize the food grains which we grow. So these are the rice, bajra, wheat. We want to maximize this. Right? Basically, we want to optimize the amount of water and nutrient we give to the rice, give to the wheat, so that we get the maximum amount of wheat for the least amount of nutrient and water. Same things for maize, etc., vegetables. Right? And sometimes we want to look at interactions between plant world and animal world. For instance, look at this figure, right, in which there is a mouse and a bamboo. Right? Now, you know that in Assam, every 12 years or 14 years, there is a profusion of bamboo flowering. There is a bamboo flowering event which happens every 12 years or 14 years. Now, when the bamboo plants, which are all over Assam and Northeast, when they flower, in order to eat those flowers, the rodent population, the mouse population also increases. So unless you do something about it, the mouse population has a different lifetime than the bamboo population. So after eating the bamboo, the mice which were generated in that generation have to go eat something else. And you know what they will eat? They will eat whatever they find. So it's a big problem economically, because the interaction of one sensed system, the bamboo system, and the other system, the mouse system, is also to be monitored. Right? Now, suppose you kill off all the rats. If you kill off all the rats, then the bamboo flowers will have a problem, because they will be just too many bamboo flowers, too many bamboo trees. There will be no control. So you cannot kill off all the rats. You have to do something about it, like killing off some of the rats or making them infertile, whatever, right? And then, of course, there are interventions which the enlightened farmer can do, like using drones for something in his field. Let's say spraying weedicides in the field, using tractors and automation to smart farm his field. For instance, imagine, suppose you did not have to hire anybody. If you had a tractor which could be just told that, okay, I have 800 acres of land, you will follow this pattern over this land and come back to my house on the 6th day after I switch you on. And the tractor would just go and do everything and come back. Suppose this was possible, then you can actually save a lot on laborers, agricultural field producers, etc., etc. And then you can use communication, you can use satellites, right? And you can store foods more efficiently. And you know how much of the food we produce actually spoils because we can't store it. We actually take rice and wheat and we dump it on a tarpaulin out in the open, and almost 20-25% of what we produce, and that's a huge amount given how much we produce in India, is actually spoiled because it rains on it. Mice get in, it's contaminated, it blows away, it's stolen, right? So even storage, right, and the mechanics of storage are an excellent application for sensor networks. So you can have, for instance, there is a company called Food Corporation of India, FCI, which has these bins. You must have seen those bins, huge cylindrical towers in which we store grains and potatoes and fruits, lychees, mangoes, right? Whatever. The interiors of those food towers, it is not just a container. It is a system, a climatic controlled system in which whatever we store must be kept dry, humidity free, temperature controlled, right, pest free, and infection free, so that it can be taken out in times of need, right, and used by us. So that is also a sensor network, because to check for pests, to check for humidity, to check for temperature, to check for infections, right, for all of it, you need a sensor network, and you need to control all that. So if it's getting too humid, you need to pump some dry air, or you need to dehumidify the bin or the silo. So a sensor network also comes in here. Right? This is, of course, in a small scale, we have a sensor network in our homes also. Right? We store potatoes, maybe 2 kilos or 5 kilos of potato. And when we see those potatoes getting, let's say, a fungus on them, we take them out and put them in the sun, we dry them out, and then we bring them back into the house. So we are controlling the spread of the fungus by sunning those potatoes. Well, when you have thousands of tons of potatoes, it's very difficult to take them all out and dry them and sun them and bring them back. So there must be something else. And we are a country in which there are farmers who produce thousands of tons of potatoes of a specific variety, because people like, let's say, Lay's, the people who make chips, Coca-Cola, Lay's chips. Right? Those people buy thousands of tons of potatoes from these potato farmers. So a sensor network is not just a luxury, it's an essential technical intervention in these things. And remember that we must remember, I'm not saying that you must remember, we must all remember that we are not technically, we like to pretend, but technically we are not a third world country anymore, right? we are a pretty sound economy, right? And we are doing very well compared to the rest of the world. Right? We are only improving from a year to year. Right? And we are doing that because there are so many of us. Unless we use these technologies, we will not do things efficiently. Right? So let me go to the next slide. I hope there was nothing very difficult in what I said in this slide. But it all comes from this particular verse: all things bright and beautiful, creatures great and small, all things wise and wonderful. We added senses to them all. So let me go to the next slide. Okay. I don't know. Okay. So what do we do? So the technology is to design the sensor network, to model the sensor network. Right? Very often, in our colleges, when we build sensor networks, what we tell our students is, I know what is a sensor network. It's got temperature, humidity sensors. You connect it to an Arduino, and the Arduino sends that its temperature sensor to something, and we display that temperature sensor. Yeah, in its essentials, and that's it, right? But the point is, how do you use it? All of us have heard and seen and evaluated, since we are all faculty members, we have all heard this term called smart irrigation. And haven't you heard these final year, third year students saying that, sir, madam, we will make a smart irrigation system for farmers? I'm sure you have. I have. At least 4 times a year I see a smart irrigation system. Now, how do you model a smart irrigation system? What do you use to model it? You may say that I don't model it, I just build it with an Arduino and I give marks to the student who built it, and that's it. But consider what will happen if you take that Arduino and show it to a farmer who is, let's say, having a rice field of 3 acres. What will that fellow do with that Arduino? Will he order 500 such Arduinos with whatever sensor? If he buys 500 of those sensors, what will he do with it? What will he know about his field, which he does not know already or does not address already? You might say that smart irrigation means he can reduce the amount of water. Now, you may want to consider that, is he actually controlling the amount of water which goes into his field? Or is it all that the monsoon deposits on his field is the water he gets? Now, most Indian farmers actually get all their water from the rain. So that's why they're so anxious that it should rain at the right time. Right? So in those 15 days in which they want the water, if the water doesn't come, the crop is dead. Right? So there is no question of controlling the water, pumping more water, pumping less water, pumping optimum water. So if you look at it from one angle, all those student projects which you see about smart irrigation systems, watering systems, etc., are not applicable to India, mainly because Indian farmers don't work that way. So what is the model then? So modeling is very, very important. Right? Simulation is also very important. And twinning or digital twinning, right? Making the digital model of whatever you are doing is, before you actually put it in the field, right, is extremely important. Right? So you know this word digital twins. Right? So you can have a physical world and you can have its digital twin, and you can build the digital twin inside your computer, and everything that happens in the real world, the digital twin is supposed to do. But the point is, constructing that digital twinning or the twin is itself a science. So is a digital twin in my computer going to behave the same as an actual implementation in a farmer's field? And now that is the question. We have to answer that question if twinning is going to be an important thing. Otherwise, we can have PhD theses on twinning. We can say that twinning is very important. We can applaud when somebody says twinning, saying very good, digital twins are the future, etc., etc., etc. But we will not be able to use digital twins. Because when we say digital twins, we are talking about a avatar of the actual world existing and behaving just the same way inside our computers. So what I mean by behavioral twinning is that my computer avatar should be exactly the same as my external world avatar. So when it is raining in, let's say, Singhbum district, in the digital twin of the Singhbum district, the rain should happen. You can say that, but rain happens because of temperature, humidity, wind, breeze. So the digital twin must have the temperature, humidity, wind, breeze, so that it rains in the digital twin when it is raining in Singhbum. Right? So that is what I mean by behavioral twinning. Its behavior must match the actual world. Then we need hardware. That's embedded systems. We must build, I won't say single board computers, but embedded systems, because these systems are very small systems. A potato plant maybe costs 10 rupees. So you cannot install a 6,000 rupee moisture sensing IoT system to monitor each potato plant. No farmer in this world will install a 6,000 rupee thing next to a 10 rupee plant. So the systems which we must use must be themselves about 3 rupees to 4 rupees in cost. The sensors which we use, and now we can borrow from everywhere. We don't have to actually use just the temperature sensors and humidity sensors we get on Amazon.com or let's say Mauser.in or Robo.in. We can buy or make or adapt from anywhere, including optical sensors, right, and build what are called cyber physical systems. That's just the hardware part of it. Now there is the software part of it. In those embedded systems, right, all of us have programmed an Arduino, but in those embedded systems, there must be specialized operating systems which are small, fast, specific, focused to the task. For instance, if I'm installing a Arduino in the field of a farmer, that Arduino is not the same as my laptop. I am not going to go to the field of the farmer and write my resume using that Arduino, just like I write my resume in Word on a laptop. So in the field, that embedded system or that sensor network must be very specific, very focused. Right? Take, for example, a petrol pump. In a petrol pump, there is an embedded system. And what does it do? It takes the cost of petrol and it multiplies it into the liters which you put into your car, and it gives you the multiplied amount and displays it on the screen. It's a very specific thing. So the embedded system must be that specific. Right? So we must have something which is that specific. We must have the protocols for that. And we must store the data which comes, because when you are measuring things using these sensors networks, there's a lot of data. And you must be able to visualize that data. For instance, suppose I say, what is the spread of COVID in India? Now, let's say I give you a table of all COVID positive cases which have been reported today since 9 a.m. in the morning. So you look at that huge table and say, well, how do I make sense of that? How do I make sense of this? But let's say I give you a map of India and I draw portions in red saying there are a lot of COVID cases here. And I draw portions in white saying there are no COVID cases here. I draw portions in blue saying there are some COVID cases here. When you look at that map, you can take one look and say, oh, COVID is going up in Maharashtra. It's going up in Kerala. But there are no COVID cases in Himachal Pradesh. I mean, this is visualization. When you have a large amount of data, the human mind comprehends it only when it is visualized well. And for each sensor network, you need to reimagine how to visualize that data. For an agricultural application, there might be a different visualization. For a factory, a different visualization, right? For human beings, different visualization, right? And then ruggedization. Come to the same final year project which you have seen ad infinitum, ad nauseam, right? Are those rugged? Can you bury them in the sand? Will they survive 3 years in the sun? Can somebody step on them and still they will go on working just like they do? Now, this is not something we concentrate on. There is a final year student who is taking something from an Arduino and putting it into a beaker of water, and we see that a multimeter is changing. And we say, very good, you are definitely A grade. No, that's not it. That's not an engineering prototype. An engineering prototype needs ruggedization. That's an important part of the sensor network. To make it, let's suppose you're putting it on a bull. Now a bull may sleep on it. And suppose you say, no, he slept on it last night and my embedded system is now powder. That can't work. Right? You have to make it so that it will resist a bull's weight, which is 1.8 tons. Right? So that's another aspect of it. Now, is there anything which we can sort of take a bird's eye view? Yeah, there is a bird's eye view of this. So you collect data from somewhere, you transmit the data, then you ingest, which means you interpret, massage, understand the data, then you store the data, and you visualize the data. So most sensor networks, right, consist of these 5 blocks only. Mostly we concentrate on this collection and storage, but there is a transmission, there's an ingestion and visualization, which is equally important. So I would say we do not give equal importance to all of these. Now, these can be actually put in what is called a stack. Right? We know stacks from networks. We know that in networks, there are 7-layer stacks. Right? Physical, data link, network, transport, session, presentation, application. So if you look at that stacked model for anything, let's say an Internet of Things thing, which you're going to put in a farmer's field, then you will have a stack which you can build for the device itself. It will have an operating system. It will have an abstraction layer. That is, whatever hardware it has, you have to abstract that hardware so that your applications and your operating system can use it. And then you will have field protocols and IoT protocols. Field protocols for communication, IoT protocols for interfacing. Right? And then you must communicate those to the remote storage, and all of these stacks must be managed. Right? As you can see, this is the very most basic thing, but it appears again out here in the gateway. So when you have a device which, let's say, senses a temperature, pushes it into a gateway, the gateway pushes it into a storage platform. Now this word called, there are 2 useless words in these 3 words. One is called IoT, that's the useless number 1. One is called cloud, which is the useless word number 2. Right? Platform, so anything is a platform. Right? Now, IoT and cloud have become fashionable words. Right? So if you say I'm doing SCADA, or if you say I'm monitoring an analog parameter using a to D converter, people will say, that's boring. Okay. Suppose you say, no, I'm not monitoring an A to D converter. I'm actually doing data aggregation and analytics with machine learning. So everybody sits up and says, yeah, machine learning, that's great. That's the thing which I was after actually. Right? So you see why all these colleges nowadays have not just plain vanilla computer science, but computer science and AI, computer science and ML, computer science and cybersecurity, computer science and data science. I mean, it's not that they have discovered some new variant of computer science. They are merely cashing in on a cash cow. Right? Every computer science student is going to do some AI course or the other. Every electrical and computer science student is going to do some machine learning course. As next to probability and statistics, they're going to do machine learning. but making it sound as computer science and machine learning makes it very good. So that's why I call this a useless word. Internet of Things is nothing but the next generation of SCADA, right? But it sounds good. People like it if you say it. So you succumb to the lure of saying Internet of Things rather than saying something from which I am taking data. And these are the stacks. You get tools, you get ontology descriptions, and you have security, which is something you get. You don't have to buy these things. So let me go to the next slide. For instance, I describe a Eclipse IoT stack, right? So you have the end devices, you have Concierge, Edge, Voto, and Hawkbit. This is for the device side, what Eclipse gives you. You have services, right? Like Hono, like Kura, or again this is for the interfaces to the cloud. And then you have protocols, right? Like Mosquito, Paho, OM2M, Leshan, Wakama, Ponte, CF. These are all protocols which are freely available to you. You don't have to buy them from anybody, right? So if you take these from the available as downloads, you actually have everything you need for a sensor network in place. You don't just have to restrict yourself to an Arduino and somebody sensing temperature or doing X or Y. Okay? And in the devices, you can run C, C++, JavaScript, Python, Java, Rust, right? And in the gateway, you can run Java, you can run Python, you can run C, you can say JavaScript, React, TypeScript. In clouds, you can also run all of those, plus Golang, plus Julia, right? So you can run all of these languages, right? And all of this is free, by the way. So you actually, I'm running out of time. I'm supposed to end at 1 o'clock. So if you look at what we do, right? For instance, what my group does, and I'm really speaking, I'm a electrical person, right, with an interest in optics and sensing. So we work on agriculture, we work on animal husbandry, I work on wildlife, right? And we work with others and on socially relevant projects, research projects, which are unique to countries, unique to geographies, right? For instance, a project of like tracking snow leopards. It's very country specific, Afghanistan. Very geography specific, Karakoram, right? So we participate in those horizontals where we have some expertise. We don't do everything. And we look at what we call clutch brake accelerator initiatives, right? With industries on both sides. Right? I mean, I think it says the Indian and Australian side because this slide was originally made for the University of Queensland, right? But it actually means any university, right? Any foreign university, any foreign organization. So I will stop here. It's 12:55, and I will ask you to ask me questions. Yes, you can ask me questions. Please ask me questions.
Anybody has any question? Please ask.
I think I was not comprehensive or boring enough.
No, sir, not like that.
I should have been more boring. I should have taken.
So it was really interesting, very informative.
Okay. But if there are no
any question? Sir, I have one question. Sir, regarding your smart agriculture, or smart irrigation. My question is that can we incorporate artificial intelligence with the smart irrigation system? Like say, what I have to say, suppose we are gathering the data of from moisture sensor, temperature sensor, or humidity sensor for last 2-3 years. Okay.
Yeah.
We are collecting the data and then we are training the system to predict the future weather. future, what will be the say humidity or temperature in the rest of the time for the
Yes.
near future, and accordingly can we plan our irrigation system? That is my question.
There are at least 3,000 scientists in Mausam Bhavan whose bread and butter depends on this, and whose children go to colleges based on the success of what they put out to this nation. So Mausam Bhavan does exactly that, except that they don't use last 3 years, they use last 30 years to 40 years of data to say what will happen in the next 6 months. Right? They are mostly right, but they don't really predict it by just looking at temperature, humidity, etc. They have a lot of variables, right? So because they have so many variables, they must run it as a simulation using big computers, right? And modeling techniques to to incorporate local variations. So what are we call perturbations in the model, right? For instance, monsoon is supposed to happen like this, but because there was a cyclone, it did not happen like this. So which state will now not get rain? So this is an answer only a perturbation-based modeling will answer. If you look at any AI model, it cannot predict outlier data like this, which is very important to the farmer. After all, he or she is interested in whether it will rain in these 15 days or not. He's not going to get a PhD out of it. But Mausam Bhavan exactly does that only. The problem is that what I encounter in projects nowadays, whether they are DST projects or student projects, is can I put a Arduino, put my things into a database, and then can I use AI models which are available, right, and get a job. So the farmer is actually incidental. What is the important thing is my getting a job in the placement. I should be able to say I work in AI, data sciences, etc. So my concern really in engineering students nowadays is they somehow want to push the word AI into their resume. They are not really concerned about smart irrigation, farmer, data gathering, understanding. No, that's my take on this. But yes, your question is very valid. It's an important activity.
Anybody, any question? Deepika, please continue.
Any participants, any question? Or should I say end the session? I think there is no more question. Thank you, sir. Thank you, Professor Dr. Subrat Kaur, sir, for his wonderful and informative speech. So our second day's first half is now ended here. We will start our next session from 2:30 south. Thank you all. Thank you all the participants, all the professors and dignitaries present. Thank you, sir.
Sir,
I think Triveni sir has some question. Triveni
yes,
sir.
sir.
Okay.
Can I check my slides once, whether they're okay or not?
Yes, sir, sure.
I think Triveni Prasad Banerjee has raised a hand, probably for me.
Yes. Triveni sir, have you any question?
Unless he wants to see Dr. Simadri's slides.
No, I don't think so.
So, Mr. Banerjee, would you have a question for me or for Dr. Simadri?
Am I audible, sir?
Of course, yes.
Yes.
Okay. The question is that how the data fusions can be improved, particularly when we are gathering the multi-sensor data. On the data, how the data can be sensor fusions can be done, and the fusion technology can be advanced, technology can be adopted.
Okay. It depends on what you mean by fusion. If I'm measuring 30 temperature values, I don't think fusing them is very difficult. We understand how to fuse 30 different temperature values, aggregate them, normalize them. I think that's not the issue. The question becomes a little difficult to answer when you talk about semantic fusion, right?
Yes, sir.
So if you say semantic fusion, for instance, Tribeni Banerjee slapped Subratkar. Right? That's an action which has a context. Right? It means something if I say Tribeni Banerjee is inherently a violent man. Right? And let's say in that little interval of time, Professor Sarit Pal also slapped Subratkar, Deepthi also slapped Subratkar, and 25 other people also slapped Subratkar. Right? Now, that also could mean that 25 people, Subratkar was surrounded by 25 violent people. They all slapped him. He is socially outcast. Right? That's the meaning. But suppose you wish to fuse it with a context. That is, there were bees attacking Subratkar, and all these people were trying to save him. Then the fusing of this data called slap becomes a different in context of that semantics of why they were slapping Subratkar. They were trying to kill the bees. Right? Do you understand? Every data piece must be understood with a context, right? And an environment in which it is to be fused. So humidity has a context, temperature has a context, actions have a context. So semantic fusion is a more difficult thing. It depends on what twin of the actual world you are talking to. Right? You understand? So that fusion is a little bit more involved in its answer than just a simple interpretation of why you were slapping me.
No, actually, sir, you have shown the last slide that you are working on the systems. Those are actually working with machines conditions monitoring. So that conditions, particularly that when I am talking about the conditions checking and sensor has to machines conditions particularly.
Yes. Yeah,
So
mostly we'll talk about vibration monitoring and
yes, yes. There is
sensing
one
of.
is vibrations monitoring, and
Yeah.
what are the
So
other
because it is
parameters
in
can be?
context of vibrations, it is not so difficult to fuse different types of vibrations. So, but if it was in other contexts, then we would have to have a different approach. But what we do in condition monitoring is vibration monitoring.
Only vibrations, no sir?
Only vibrations.
Okay, and if there is different kinds of vibrations, then only the signal processing technology will be taking care of.
Mostly, yes, mostly. But we do extract features, we do machine learning on that. So I can't say it is only signal processing we do, but it is definitely the feature extraction is from vibration data.
Okay, and can you suggest, sir, any other parameters can be taken care of?
Well, machines vibrate. That's the only thing which you monitor in a machine. Right? So even when your
And
kitchen mixie starts
current
giving out
parameters also can be taken care, sir.
well, the machines we monitor in my lab are mostly rotational vibration machines, right? Engines. So we don't monitor anything else. Acceleration and vibration, that's it.
Accelerations and vibrations, no sir?
Nothing else.
Okay, okay. So can I ask you one another question is out of track actually. Can you know Professor BK Panigray?
Yeah, he's in my department.
Yes, sir. Yes, sir. He is very close to, friends of me actually.
Very nice. He's a nice human being.
Yeah. Thank you, sir. Thank
He's
you for
also
your
head of the department, actually.
yes, 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 yes. He is currently in probably in the department of electric vehicles like that, no?
Yes, CAPAT.
Yes, Kapat.
It's called CART, actually.
Yes, CART.
Center for Automotive Research.
Yes, sir. Okay, sir. Nice to meet you, sir. Nice to meet you, sir. Thank you.
Thank you. Bye-bye.
Okay, bye.
Thank you, sir. Thank you. So our today's first half session is ended here. We will start our session in second half from 2:30 sharp.
Bye.
Sir, have you checked your slides, sir? Professor Reddy's.
Dr. Reddy, sir? I think he has checked, I think. It was working. Just I am asking. Deepika, just I am asking Dr. Reddy. Okay.
Okay, sir. You ask first, then we will lead. Sir, please unmute yourself.
Yeah, he was checking, and I have seen that it was working. Okay.
Okay.
So we can proceed for the next session from 2:30 p.m.
Okay.